So this lab is broken up into two pieces. So there's two parts to the lab. The first part deals with part one. Let me be careful here. Parts 1, 2, and 3, they deal with pressures and fluids. So we're really using the ideas of fluids. Part 4, we're going to deal with atmospheric pressure and we'll deal with the ideas of the ideal gas law. So I will only lecture about pressure and fluids today, and then next time I will do that. So let's make some definitions. The first definition is that pressure is defined as force divided by area. And so when you look at this thing, the units of pressure, they go by the symbol P. So it would be a unit of force and a unit of area, which would then be a Newton per meter squared. And this is defined in terms of a Pascal. So to get a physical sense of a Pascal of pressure, imagine that you have a table. So this is your table right here. And what you're going to do here is that you want to set the dimensions of the table to be a meter squared, which is effectively a 3-foot by a 3-foot table. So that means here is that the area that we've chosen here is 1 meter squared. Now, I need a force, and typically when we think about a force in these situations, we're thinking about a weight, and here we need 1 Newton, and that's approximately a stick of butter. Now, if you were to take this stick of butter and make sure that it's soft butter, and you put it all the way across the table, you're going to find that the pressure acting down on this table, the pressure in this case would be 1 Pascal. So that's not very much pressure. So 1 Pascal of pressure is extremely tiny. So we need better units for everyday situations. So a better unit for everyday situations are, they call them atmospheres, ATMs, an atmosphere or atmospheric pressure unit. So for example, your car tire has about 2 atmospheres, a little more than 2 atmospheres inside your tires. So how do you get atmospheric pressure? So by definition, one way of defining atmospheric pressure, it's going to be the weight of air divided by, let's say, 1 meter squared. We could take a table, just like we did up above and did that. We could look at a rectangular thing. Another thing that would be useful is if you were to take a sewer pipe. I think I've seen some sewer pipes that are about 1 meter, they're about 1 meter squared. So if I was to take a sewer pipe, and if I was to have all this air all the way up to the top of the atmosphere, so to the top of the atmosphere is about 40 kilometers. And in here, you have all this air. And so what you would expect here is that the density of the air is thickest, down closer to the surface of the earth. And as you go up, it gets thinner. So it's not you have to look at how you get the density. But if you were to weigh this column of air, okay, so if you look at the weight of this column, it turns out to be 22,500 pounds. But in the metric system, it's about 100,000 newtons. So then we can then define atmospheric pressure. So atmospheric pressure is typically written as PATM, and this would then be the weight of the air in this column divided by 1 meter squared. So this would then be roughly 100,000 newtons per 1 meter squared. So this is 100,000 pascals roughly for atmospheric pressure. And that turns out to be a really important number in this lab. Now, there are other units for atmospheric pressure. So we could say that we have 1 atmosphere, and 1 atmosphere, it's a little over 100,000. It's really 101,000 pascals. And a lot of times you'll hear news people, they typically call them in kilopascals. And another one is 14.7 pounds per square inch, where this guy, the pounds per square inch, is literally written as pounds per square inch. Now, what's a useful measure of atmospheric pressure? So this is a useful measure because you can feel this. And in the lab, there's something called a pressure bar. And that pressure bar, you have to hold it. There's no way around it. You got to hold that pressure bar. That's 1 atmospheric. So that means atmospheric is roughly 15 pounds per square inch. So you would be holding a square inch on your hand. That's 14.7 pounds. So let's go to the lab here. So we'll define other things as we go along, but in part 1, what we're really looking at is we really want to pay attention to pressure and atmospheric pressure. So we're really, I think in the first one, we're going to be looking at pressure and atmospheric pressure. Now remember, the way I'm going to write atmospheric pressure is that I'm going to write it PATM. So there's 3 parts on this thing here. So in part A, we want to estimate the pressure on a poster on a table. Now, we know how to do that. And the way we know how to do that here is because we could measure this. We could set up the poster in, let's say, square inches. So if I have a poster, let's say it's this big, and each of my squares right here is a square inch. So in other words, from here to here, this is 1 inch. And then from here to here, this is 1 inch. Then you know for a fact that this square right here has to have a pressure of 14.7 psi. So if I add up the squares, I can estimate what that pressure is. Now, if you calculate the pressure in, 14.7 psi, the standard thing to do here is to convert into pascals. Why? Because we measure things in pascals. So that's one way to think about that. Now, the other thing that we want to look at in part B is that we want to look at human blood pressures So human blood pressures and getting a feel for it. Right? So when we're talking about pressures, we're typically talking about pressures of what? 120 and 80 as these human blood pressures. So the question is, can you get a feel for what that pressure is? So to get a feel for it, we want you to squeeze. We want you to squeeze a bag to reach 120 and 80 to get a sense of what that feels like. Okay, so remember, these units are, of course, in millimeters per mercury, but we can change those immediately to pascals. Okay, and the conversion, which I didn't do that before, is 100. So 1 atmosphere is also 760 millimeters of mercury. But that's to give you a sense of what is going on. Now, the other thing that we want to look at here is in part C, is that you're going to be dealing with syringes. And the key thing about syringes is that if I have a system where the pressure is a constant, then according to this, how much force you have to apply is then going to depend completely on the area. So in other words, if I increase the area or if I decrease the area, then the forces have to behave similarly. So in essence, if I have a syringe that has a bigger diameter, and I'm going to be pushing on that syringe, right, and saying that this is what you're pushing down right here, versus one that's going to be thinner, what would you expect in the pressure or the force, excuse me, in this system? How are they going to behave? So remember, a lot of this is experience. Okay? A lot of this is experience. Let's go to part 2 here. Part 2 here is a lifting water station. One of the things that you need to think about when we start talking about pressure is that pressure systems always move from high to low pressure regions. So there's a couple ways that you can think about this. And as an example, suppose you drink soda from a glass with a straw. So how does that actually happen? So you could imagine that you have your glass, and then what you've filled it with is that you have orange soda. And then what you're going to do here is you're going to take your straw and you're going to put it into the glass. So when you put it into the glass, here's what you're actually seeing here. What you're seeing is that up above here, the side view, you're going to have some soda in the straw. And the whole goal here is that you're going to do what? You're going to put your lips around that straw. And oh man, I don't even know how you would draw lips. But we imagine that, wow, let's not even try to do that. So what you actually do right here is that inside the tube is that you have air. And what you're going to do here is that you're going to pull, right? You're going to draw air out of the straw. And what you're finding here is that down at the bottom of the glass is a high pressure. And as you pull air out of this, you create a low pressure. And as a consequence, the orange soda then moves up because you're moving from a high pressure region to a low pressure region. And so when people say, well, I sucked soda up, well, that's not true. You reduce the pressure in the straw, and then what happens is that gravity pushes down on the surface. Okay, the force of gravity pushes down on the surface of the soda, and as a consequence, it then forces the soda to move upwards. So reducing the pressure allows gravity to push it down and then go up. So now a question then comes up. What happens if one makes the straw longer and longer? is there a maximum that one can draw soda, a maximum, I should have said a maximum height that one can draw soda from a straw. And that's exactly what is happening here. The idea here is that there is a maximum height. And the maximum height, max height, one can draw soda up is determined by gravity's ability to push down and the pressure difference maxima. And so what you're finding here is that we all have a sense that pressure is depth dependent, right? So we could say that pressure differences, this is depth dependent, because if you jump into a pool, let's say of 10 feet or 12 feet, and you go down to the bottom, you can clearly feel it in your ears. So it has to be depth dependent. And it turns out that the way it's depth dependent is that it's equal to, this change in pressure is equal to the density times gravity times the depth. And a lot of times people write this as the density with rho, gravity, and then the height change. And it turns out you can only get max with this height change. So it depends on the pressure difference. So the way we want to do this today is that we want to check this with the parking garage. And the way we want to deal with the parking garage is that we have a long straw. So if you're at the top of the building, what we'll do here is that there's a way, there's a balcony where you can actually tie the tube. So if you tie the tube or the straw, and you'll see that the nice thing that's done about this is that there is, I believe it's red tape, and it marks every, I don't remember, is it every 5 feet, I think? I don't remember how many feet it is. Maybe is it every 1 foot?
I think it's every meter.
Every meter. Yeah, I'm sorry. Why would I say feet? It's every meter. And what you'll find here is at the bottom, you'll have a bucket. And the bucket, if I remember correctly, has green colored water. So it's easy for you to see here. Now, up at the top here, we're going to attach a pump. So when you're looking at the pump, the whole goal of the pump, of course, is to take air out of the tube. So the pump replaces your mouth for drawing air out. So the whole goal here is that you're pulling air out with the pump. So if you're pulling air out, now I create a pressure difference. And when you create this pressure difference, what we should see here is that it now plays the same role as how we draw, how we replace, how we take water up a straw. So in this case, as we take the air out, now gravity comes in, and what does it do? It pushes down, and then it pushes it up, and then it pushes it up the tube, and the maximum, I should have looked this up, it's somewhere around 10 meters, which is going to be around 30 feet. It's a little bit more than 30 feet. My mind tells me it's like 33 or something like that. But that's the idea. Do you get to that maximum height? And a lot of it depends on this pressure difference. The only way you can get this pressure difference, this max pressure difference, is if this initial pressure, you have to be able to get to essentially absolute zero in that pressure in order to get that maximum height. So that's a little bit of a field trip. Let's look at the last part here, which is part 3. Part 3 is Archimedes' principle. There's a lot of history with Archimedes' principle. He's definitely one of my favorites. You've probably heard the story of the crown and the word eureka. Yeah, this is a guy, and this is a pretty ingenious little thing. And here's what we got to do. What we need to do here is that we need to define what a buoyant force is. And what you'll find here is that a buoyant force, it's caused by a pressure difference caused in fluids. And so if I have a block, let's just say that we have a rectangular block here, and this block here is submerged in water. So since water is pressure in water is depth dependent, you could see that this is going to be a low pressure because it's not that deep. The bottom part of this is going to be a high pressure. And if the areas are the same, then the force at the bottom, which is going to be, let's call this pressure 2, let's call this pressure 1, this will be pressure times the area, and then the pressure at the top here will be the pressure of 1 times the area. And you'll see here that a free body diagram shows that you're going to have a pressure, a force, a net force that goes up. And this net force is what they call the buoyant force. So the buoyant force is really the force from the bottom minus the force from the top. And again, this is caused by a pressure difference. Okay, so this, again, this is due to a pressure difference. So that's how we define what a buoyant force is. And you have experience with this because, as an example, if you put a, let's say I don't know, a beach ball and what do? We submerge it what ends up happening here is that you feel the buoyant force pushing the ball up. That is the buoyant force. So now, what does Archimedes' principle says here? So Archimedes says this, that the magnitude of F of B, the buoyant force, is equal to the weight of displaced fluid. So if you can measure the weight of the displaced fluid, you have a way of predicting what that buoyant force is here. So what we want to do here is that we want to compare two values. We want to compare the buoyant force, and we're going to measure this versus this, and I'm going to call this the weight of the displaced fluid here. So there's two techniques. So this one I'm going to call number one, and then this one I'm going to call number two. And then we want to compare them. So how do we do this here? What we're going to do here is that we're going to take our object. Let's say that this is our object. And we're going to attach this to a string. And up here, we're going to have some type of mass scale. Or maybe it's a Newton scale, I don't know. But you're going to have some spring scale that's going to measure this. And what you're going to do here is that this is going to be measured in air. So in other words, you're going to get the force of this guy, the weight of this guy in air, which will then be mg in air. Now what you're going to do here is that you're going to submerge the block into water. So now that means I'm going to have the same thing with the same block, but now you're going to have this in a container of water. And what you're going to find here is that this container of water here, you're going to see that this is now going to be the force in water. And you're going to see that there's going to be a difference between the two. So the difference between the weight in air, which will be heavier, and the difference between the weight in water, which is the buoyant, it's a combination of the buoyant force here, you're going to see that we could measure FB experiment by looking at the difference between that in air minus that in water. It's going to look like it lost weight.
And you are going to be using these green scales, which are calibrated in Newtons. That's not Kelvin. So we're good.
So then the next thing here is that we need to measure the weight of displaced fluid. And the way we do this is that we have a system. we have canisters that have little spouts. And what you do here is that you fill it up right till the edge right here. And then what you're going to have here is that you're going to have a catcher. And this is where the overspill of water is going to be caught. So now what you're going to do here is that now you're going to insert the block. So when you do that, what actually happens? So if I copy this and put it over here again, what you're going to find here is that now you have your stream and it comes in here, and then the block now raises the level of the water and water starts pouring out. At some point, the water is going to stop flowing because it doesn't get up to that one point, but guess what? That's the displaced water. So now, weigh that water. So remember, so in the weight scale, so when you use your mass scale, be sure to zero out the water container so that the mass scale only reads the mass of the water. So now you have that. Now you have the weight of the displaced fluid. You have a number. So the question that we've already asked here is that, are these guys the same? Check Archimedes' principle. So if I would come down here, I would then say, check this principle. Does it agree with what you measured?